Our project is a smart cargo operating unit with tethering, also known as Scout, with Kentrell Hardemon-Pace, Kehlana Brooks, Sam Orozco, and Devani Trent. So why Scout? The problem that we have identified is manual material handling, and it is one of the leading causes of workplace injuries in industrial and warehouse settings. And current solutions cost tens of thousands of dollars. So Scout is a self-navigating car that autonomously follows a designated operator, reducing physical strain and speeding up material transport without expensive infrastructure or full autonomy. And the key features include location tracking, load sensing, speed control, and an LCD interface. So our basic objective is to track user via UWB-based relative positioning, maintain sufficient tracking accuracy, avoid obstacles in real time, enable smooth following behavior. And our goals include autonomously follow a designated user's UWB tag, maintain a minimum distance of 1 meter, use 3 UWB anchors for positioning, avoid obstacles via mounted ultrasonic sensor. And going into our advanced objectives, they include a closed-loop motor control system, adapt speed to payload weight, smooth acceleration and deceleration, and built-in safety limits. And our goals include load sensing integrated in a fixed bed, speed capped at 1.1 meters per second once payload exceeds 1 pound, and speed kept at 0.75 meters per second at max payload, which is 10 pounds. So going into our engineering requirements, it includes a localization method, which will be ultra-wideband or UWB relative positioning, a following distance of no less than 1 meter, a maximum speed of 1.5 meters per second, speed limiting method of load-based dynamic motor speed scaling, an obstacle detection method using an ultrasonic sensor, an obstacle detection range of up to 2 meters, a payload capacity of up to 10 pounds, and a battery life up to 45 minutes of continuous runtime, and an obstacle response time of less than 200 meters per second. And the 3 engineering requirements highlighted will be demonstrated in the demo. So going into our component specifications, we have a UWB localization module with plus or minus 10 centimeter relative positioning, SPI communication interface. Then we have a battery pack with a nominal voltage of 12.8 volts using a lithium iron phosphate, a battery management system of 40 amps, and protection for overcharge, over discharge, and short circuit, a load cell sensor, measurement ranging from 0 to 10 pounds, and a motor drive subsystem of a nominal range of 12 volts.
Now that the full cart is operating, we can demonstrate how the load sensing system affects the motion of the vehicle. With less than 5 pounds on the platform, the cart is allowed to operate at its normal maximum speed. Once the measured load reaches 5 pounds or more, the ESP32 automatically lowers the maximum motor speed. This reduces the cart's acceleration and overall travel speed while it is carrying a heavier load. The purpose of this feature is to improve stability and safety. A heavier payload increases the momentum of the cart and requires more distance to slow down or stop. By limiting the speed based on the measured weight, the system reduces sudden movement and helps prevent the load from shifting. This demonstrates how the load cell, HX711, ESP32, and motor control system work together as one complete system rather than separate subsystems.
For this demonstration, the robot is being controlled using the Citroen MDDS30 motor driver instead of our custom motor driver PCB. While the hardware is different, the overall control architecture remains the same and demonstrates how our final system is intended to operate. The ESP32 acts as the main controller by generating PWM and direction signals for the left and right side of the robot. These signals are sent to the motor driver, which controls the power delivered to the motors. In our custom design, this function is performed by the DRV8701 gate driver and external MOSFET H-bridges. In this demonstration, the MDDS30 performs that same role by receiving PWM and direction signals from the ESP32 and driving the motors accordingly. Another important similarity is the drivetrain configuration. The left motor output controls the 2 left side motors connected in parallel, while the right motor output controls the right side motors connected in parallel. This is the same configuration that our custom motor driver PCB was designed to support, allowing independent control of each side of the robot for differential steering. As the demonstration begins, the robot responds to commands generated by the ESP32, which are sent to the MDDS30 motor driver to control the motors. In this video, the cart is shown driving forward to demonstrate that the control system Motor driver and drivetrain operate together as intended. The left motor output drives the two left side motors connected in parallel, while the right motor output drives the two right side motors connected in parallel. This verifies that the ESP32 is successfully controlling both sides of the drivetrain using the same differential drive architecture that our custom motor driver PCB was designed to support. Although the MDDS30 is used for this demonstration, it serves as a functional replacement for our custom motor driver PCB during system testing. The same PWM and direction signals, the same ESP32 control logic, and the same parallel motor configuration are used in both designs. This demonstrates that our overall motor control architecture is sound and provides confidence that our custom PCB is capable of performing the same control functions once fully integrated.
The system also incorporates a battery monitoring feature to provide the operator with real-time information about the remaining battery capacity. A voltage divider on the main PCB safely scales the battery voltage to a level that can be measured by one of the ESP2's analog to digital converter inputs. In this case, the GPIO pin was GPIO 4. The ESP32 continuously samples the voltage, calculating the corresponding battery percentage based on the discharge characteristics of the lithium iron phosphate battery. And as you can see on our LCD display, we are displaying a battery percentage of 89% currently, which is around 13.3 volts. The cart will be powered by a 12.8 volt lithium iron phosphate battery, which supplies power to the entire system. The battery voltage is routed to our custom regulator PCB, where the LM2596 buck converter steps voltage down to a regulated 3.3 volt supply. The regulated voltage is then sent to the main PCB to power the ESP32 and the rest of the low voltage electronics. The ESP32 acts as the brains of the system, communicating with the UWB modules, the HX711 load cell interface, the LCD display, the ultrasonic sensors, and the motor driver. It continuously processes sensor data and generates the control signals that allow the cart to operate. Mounted beneath the top platform is the load cell that measures the weight on the play load placed on the cart. When weight is applied, the load cell produces a very small analog signal that is proportional to the applied force. Because the signal is only a few millivolts, it is first sent to the dedicated HX711 amplifier board, where it is amplified and converted into a digital signal. The digital data is then transmitted to the ESP32 on the main PCB, where a calibrated conversion factor is used to calculate the actual weight. Finally, the measured weight is displayed on the LCD in real time, allowing the operator to immediately see the current payload. In addition to displaying the weight, this measurement is also used by the control software to reduce the car's maximum speed as the payload increases, improving overall safety. As you can see, the phone weighs about half a pound and is displaying 0.58 pounds.
The positioning system for a Scout uses ultra-wideband technology, or UWB, which is a radio communication protocol that measures distance with centimeter-level accuracy by calculating the precise time it takes for radio signals to travel between devices. Our system consists of 3 custom PCBs mounted on the cart, 2 ranging anchors, and 1 relay anchor, and a 4th PCB worn by the user acting as the tag. Each board is built around 2 main components: the ESP32 Room 32E microcontroller, which handles all the processing and communication, and the DWM3000 ultra-wideband radio module from Qorvo, which handles the actual distance measurements. The board also includes a AMS 1117 voltage regulator to step down from our 9-volt battery input to the 3.3 volts required by both chips. For the ranging protocol, we use double-sided two-way ranging. In this protocol, the tag initiates communication by sending a poll message to an anchor. The anchor responds with a response message. The tag then sends a final message and calculates the distance between the precise timestamps of each message transmission and reception. Because the messages travel at the speed of light, the time of flight between devices can be used to calculate distance with centimeter-level precision. The double-sided approach compensates for clock drift between 2 devices, making the measurements significantly more accurate than single-sided ranging. In our specific implementation, the tag ranges with both the left anchor and the right anchor sequentially. Each anchor measures its distance to the tag independently. One of the anchors also acts as a relay anchor. After completing its ranging exchange, it forwards the distance data to our main ESP32 microcontroller using ESP Now, which is a lightweight peer-to-peer wireless protocol built into the ESP32. The main ESP32 then uses the two distance values, one from the left anchor and one from the right anchor, to determine both how far the user is from the car and whether the user is to the right or left. This directional information is then passed to the motor control system to steer and drive the car toward the user.
Overall, this project successfully demonstrates an autonomous material handling cart that integrates UWB localization, obstacle detection, load sensing, battery monitoring, and custom design electronics into a single system. By combining these technologies, we've built a reliable and scalable platform that improves the efficiency and safety of material transportation and warehouse environments.